next part of the dissection will be concerned with the ventricle system and the basal ganglia. And it is in the ventricle system, as you know, that the cerebrospinal fluid is formed, in the choroid plexa. And the largest choroid plexa are located in the lateral ventricle. Look here on the cross-section. The lateral ventricle is transected in two places, up here in the main part, and also down here in the temporal lobe. Why is that? Well, it often helps to see how structure has developed. And as you know, the central nervous system, the brain and the spinal cord, comes from the neural plate, which in the early embryonic stage develops into a neural tube. Look here. The development is rather complicated in the rostral part of the neural tube, where a series of primary brain vesicles and flexures develop at an early stage. As neurons multiply and structures differentiate in the wall of the brain vesicles, the large cavities are gradually transformed into the brain ventricles, represented by 4 narrow cavities in the fully developed brain. The most dramatic changes take place in the telencephalic vesicles, one on each side. They expand rapidly, like this, and will eventually cover most of the rest of the brain. Look down here at the drawing from about the 3rd month of pregnancy. The pronounced development of the posteroventral part of the brain in a downward and forward movement forms the temporal lobe, which is such a characteristic feature in the fully developed brain. The configuration of the ventricle within the hemisphere can best be understood if you conceive of the development of the temporal lobe as a semicircular expansion of the hemisphere. In other words, if the cavity within the developing hemisphere is projected here on its lateral surface, if it looks something like this, and with the development of the temporal lobe, the cavity, which can now be recognized as the lateral ventricle, will also take on this semicircular shape, like a horseshoe, like this. At the same time as it becomes increasingly more narrow as the different structures take shape in the hemisphere. If we now cut the frontal section through the hemisphere like this, the lateral ventricle will be transected here in its central part. Look over here in the cross-section of the brain. Here it is. And it will be transected down here in the temporal horn. Look again here in the cross-section of the fully developed brain. One part of the basal ganglia, namely the caudate nucleus, is closely related to the lateral ventricle in the hemisphere, and it will also be affected by this semicircular movement and development of the temporal lobe. Look down here. The main part of the caudate nucleus, the head of the caudate nucleus, is located here in the floor of the lateral ventricle, like this. And its tail, the tail of the caudate, describes a semicircular curve similar to that described by the temporal horn of the lateral ventricle as it reaches into the temporal lobe. Since the caudate is located in the floor of the lateral ventricle at this level, it will be located in the roof, in the temporal horn here. Look again in the large drawing. Here is the caudate nucleus in the floor of the lateral ventricle in the central part, and here it will be located at about this level in the roof of the temporal horn. In our dissection, of the ventricle system, we will now start to cut horizontal sections down like this until we reach the dorsal surface of the corpus callosum. And we will then open up the lateral ventricle by removing here part of the radiation of the corpus callosum, which serves as the roof of the lateral ventricle. And that will enable us to inspect the floor of the lateral ventricle at this level, where caudate nucleus, the colored red here, is located laterally, and thalamus in blue is located medially. It is maybe a little surprising to encounter thalamus here in the floor of the lateral ventricle. After all, thalamus is a diencephalic structure, whereas the lateral ventricle here represents the cavity in the hemisphere, which is a telencephalic structure. But the explanation for this is the following. The dorsal surface of the thalamus is at this point covered by a thin ependymal layer here, which belongs to telencephalon here. So, in reality, we are looking at the thalamus here through the very thin wall of the telencephalon here. And this very thin layer of telencephalic tissue, which covers the dorsal surface of the thalamus, is referred to as lamina affixa thalami. And this ependymal layer continues onto the surface of the choroid plexus at this level. I have exaggerated the drawing in this region in order to be able to explain the anatomical relations. When we dissect the brain, you will realize that the fornix, colored yellow here, is in reality lying rather tight on the dorsal surface of the thalamus, with only a thin layer of connective tissue in between. In any event, the choroid plexus in the central part of the lateral ventricle here represents an invagination into the ventricle of a highly vascularized connective tissue. And this layer of mesodermal tissue here, which is called the tela choroidea, was trapped between the telencephalon and the diencephalon when the rapidly developing cerebral hemisphere and their commissural connections, the corpus callosum here, expanded backwards on top of the diencephalon. Tela choroidea, or velum interpositum, as it is also called, is not really located inside the brain. It is located here in a fissure, which is referred to as the transverse fissure, which can be reached from behind, underneath the splenium of the corpus callosum. And the location of the transverse fissure can best be appreciated on a mid-sagittal section. So let's take a look at this photograph. Here is the tela choroidea in the roof of the third ventricle, with the choroid plexus hanging down from its inferior surface. As this black arrow indicates, the transverse fissure can be reached from behind, underneath the corpus callosum, or more precisely, between the splenium of the corpus callosum and the pineal gland. In other words, one can get into the transverse fissure with a probe and follow tela choroidea all the way to the level of the interventricular foramen. And one would still be outside the brain, technically speaking. Where the transverse fissure opens up caudally, tela choroidea will be in continuity with the pia arachnoid on the external surface of the brain. Let's return to the cross-section. The two major structures within the tela choroidea are the two internal cerebral veins, colored white. There is a choroid plexus also in the temporal horn of the lateral ventricle. But at this point, the choroid plexus is continuous directly with the pia arachnoid. surrounding the brain rather than with the tela choroidea, as up here. The site where the highly vascularized pia mater invaginates into the cavity to form the choroid plexus is referred to as the choroid fissure. And it is important to realize that this type of invagination occurs along the whole extent of the lateral ventricle. In other words, the choroid plexus up here in the central part is continuous with the choroid plexus in the temporal horn behind the diencephalon. And the choroid fissure forms a semicircular curve similar to that presented by the fully developed lateral ventricle. The choroid plexus in the third ventricle is also represented by invaginations from the tela choroidea, and more precisely from the inferior surface of the tela choroidea. As a matter of fact, the choroid plexus in the third ventricle is continuous with the choroid plexus in the lateral ventricle at the level of the interventricular foramen. By the way, this part here is also part of the third ventricle. As you can see here, the two thalamic nuclei are often connected with each other by some tissue in the midline that we refer to as the massa intermedia. The choroid plexa produce the cerebrospinal fluid here, here, and here. And they are anatomically intriguing and clinically important structures. The mechanism by which the choroid plexus develops seems rather simple. The wall of the developing brain vesicles becomes very thin at one point, represented by the choroid fissure. Just an ependymal layer at this point, where it is in effect pushed into the cavity by highly vascularized connective tissue, which is directly continuous with the pia on the external surface of the brain vesicle. Almost like a fist pushed into a glove like this. In summary then, choroid plexus consists of highly vascularized connective tissue covered by an ependymal layer. We'll now review a series of photographs in order to prepare ourselves for the dissection of the ventricle system. We'll now expose the lateral ventricles. So in this drawing, we have cut away horizontal sections down to the level of the corpus callosum, and we have removed the roof of the lateral ventricle. So what we're seeing here is the floor of the lateral ventricle. The most prominent structure related to the anterior horn of the lateral ventricle is the caudate nucleus, whose massive anterior part, the head of the caudate nucleus, bulges into the anterior horn of the lateral ventricle. Caudate nucleus is colored orange in this drawing. The central part of the lateral ventricle is quite narrow. The choroid plexus, colored red, and the thalamus, colored blue, are the most prominent structures in the floor of the central part. The posterior horn extends for a variable distance into the occipital lobe. We'll now continue the dissection on the right hemisphere by exposing here the temporal horn of the lateral ventricle. To do this, here we have another photograph from the lateral side. What we have to do is to cut away the frontal and parietal opercula covering the insula here, and open up the temporal horn from the lateral side. We are cutting into the temporal lobe in the direction of the superior temporal sulcus, and we are removing piece by piece the superior temporal gyrus at this level until the whole extent of the temporal horn is exposed. The beautifully curved structure in the medial wall of the temporal horn, colored yellow here, is the hippocampus. Here's the crus fornicis behind the thalamus. And you can follow here the choroid plexus as it swings around into the temporal horn of the lateral ventricle. The next thing we will do is to take away the corpus callosum and the fornix and expose the tela choroidea underneath the corpus callosum and the fornix. And we made a transfer scat behind the gene of corpus callosum through the septum pellucidum and fornix in order to flip the corpus callosum and the fornix backwards like this. Look, the fornix, colored yellow, how the two crura fornices disappear laterally and down into the hippocampus formations of the two temporal lobes. The fibers that cross between the two crura fornices connect the two hippocampus formations with each other. That's the hippocampal commissure. Important structures in the tela choroidea are the two internal cerebral veins, one on each side. The internal cerebral vein receives blood from the choroid vein, the thalamostriate vein, and the septal vein in the front. We'll now remove the tela choroidea here in order to expose the third ventricle. But before we do that, we'll take away the posterior part here of the right hemisphere. To do that, we'll cut through the crus fornices and the splenium on this side, and we'll make a horizontal cut here in the front of the temporal lobe at the level of the lemur insula. And we can then remove this whole part of the cerebral hemisphere. Then we will very carefully strip away the tela choroidea with the two red-colored choroid plexa here. And we'll do it from the front here and backwards very carefully, and we will end up with the following picture. We will then have removed the roof of the third ventricle, so we'll look down into the slit-formed third ventricle between the two thalamic nuclei here. Here is the two habenular nuclei. Here's the pineal gland between the two superior colliculi. Back here are the two inferior colliculi.